This video will cover section 5.5, multiple angle and product to sum formulas. This is the last section of chapter 5. The objectives will be to use the multiple angle formulas to rewrite and evaluate trigonometric functions, use power reducing formulas to rewrite and evaluate trigonometric functions, use half-angle formulas to rewrite and evaluate trigonometric functions, and product to sum, sum to product, also to rewrite and evaluate, and trigonometric formulas to rewrite real-life models. So as you can see, the section, it will consist on rewriting and evaluating trigonometric functions. And the new formulas that we will be adding to our list will be, of course, the multiple angle, the power reducing, half angle, product to sum, and sum to product formulas. And they will all be used for the same purposes of rewriting and evaluating the trigonometric functions. With the multiple angle formulas, we're going to study 4 other categories. And the first one will be, the multiple angle formulas, such as having the sine of an angle times a constant. So this is like we have the parentheses here. So an example will be sine of 2x, something like that. And this is the sine of a double angle. Or the cosine of 4 times u. So that is what we mean with when we say multiple angles. The second category, squares of trigonometric functions. So things that contain sine to the power 2. Remember, this is similar to having sine of u and then square. So that's exactly what it means. And it is equivalent to saying something like this: sine x times sine x. But when the exponent is there, what you're squaring is the whole sine of u. The third category, half angles, such as sine of u divided by 2, or for example, something like angle alpha divided by 2, or any other trigonometric function. And then we also have the fourth category, which will be involves products of trigonometric functions, such as sine of u, cosine of u. So if you recall from the previous function, we were using, for example, the formula to calculate the sine of the addition of 2 angles. That was section 5.4. And it was something like the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. So here when we say products of trigonometric functions, we're referring as things like that. Here we have one trigonometric function times the other, so that's a product right there. You should learn the double angle formulas because they are often used in trigonometry and calculus. So again, this class, it's called pre-calculus for a reason. It's supposed to prepare you for calculus. So don't think that you will never see them, and especially the ones that we have here. Sine of 2u, or a double angle, cosine of 2u, and tangent of 2u. So what we're going to do is try to derive, let's derive at least the first two. So if we have sine of 2u. This is the same as saying sine of the sum or addition of two angles. They just happen to be the same, u plus u. And if I use the formulas from last section, 5.4, I could rewrite that as the product of sine of the first angle, which is u, times the cosine of the second angle, which happens to also be u. And then it would be plus the cosine of the first angle, u, times the sine of the second angle, which is also u. And so the two terms here, they are the same. They are in different order. Sine and cosine, the products. However, we could rewrite them because multiplication is commutative, so I can rewrite the second one like I'm doing here on the bottom. And now you could see pretty easy that they are the same. So we can say that the sine of 2u is equal to, if we add one of these plus another, we will get two of those. So that will be 2 times sine of u cosine of u. And so that is the first formula that we have here. Now let's see if we can derive the one of the cosine of the double angle. So I already wrote down the formula here. Remember, 2u is the same as u plus u. So I am going to use the formula from previous section, and that states that we need to calculate the cosine of the addition of two angles. It will be the product of the cosine of the first angle times the cosine of the second angle. Remember, the angles are both u. And then we need a minus, and it will be sine of the first angle times the sine of the second angle. So at this point, if we go ahead and carry out the multiplication here, we will have cosine square of u minus, and if we multiply sine of u times sine of u, it will be sine square of u. And that you could see here. Now that is, I guess we could call it one of the variations, number one. Now let's see how we can get the next two. So to get the second one, we could use the Pythagorean identity, the main one, sine square x plus cosine square x is equal to 1. So from here, what we could do is perhaps substitute this part, sine square of u, and that will be sine square of u, well, in this case, with the Pythagorean identity, it will be sine square of x is equal to 1 minus cosine square of x. So if I substitute this part here, but notice that I'm going to switch the angle, the variable, so it's going to be u instead of x. So I could say instead of sine square x or sine square u, I'm going to substitute it with 1 minus cosine square x. And what I need to do here is remove parentheses. So I'm going to distribute the negative sign. So now I'm going to have cosine square of u minus 1 plus cosine square of u. And actually, I just noticed how I use x instead of u. Make sure you don't do that on web assign. So at this point, we have 2 of those cosine square u. And this could be 2 cosine square u minus 1, and that will be the second variation to the cosine of a double angle. Now to get the third one from the Pythagorean identity, we know that if we solve for cosine square x, and let's go ahead and just switch this to u so there's no confusion. Okay, so from that identity, if I solve for sine square x, cosine square u, that will be equal to 1 minus sine square u. And now what I'm going to do from the first variation of the Pythagorean identity, the one that we found here, not first variation, sorry, the first, I guess the first variation of the cosine of a double angle. So from there, now what I'm going to substitute is cosine square of u. And I'm going to substitute cosine square u with the expression here that comes from the main Pythagorean identity. So if I do that, I'm going to do it on this side. So instead of cosine square u, I'm going to have 1 minus sine square u. Here, I mean, you could include the parentheses or not because there's a positive sign in front of it. Then I'm going to keep writing what continues here, and it's minus sine square u. And so with that, if I do combine like terms, I will have 1 minus sine square u. Well, remove parentheses. We have two of those, but they happen to have a negative coefficient of -1. So then if we combine like terms, we're going to have -2 sine square u. And of course, we cannot forget about the one that was in front of the sine square u. So then, as you can see here, we have the third variation of the cosine of the double angle. Now for example 1, we are going to solve a multiple angle equation. And so what we're going to be doing is substituting with the double angle formula for sine of 2x. And if you look at the formulas, we're going to be using the one that you see here. 2 times sine u cosine u, except that here we will use it with x. So let me just write it down here. So the sine of 2x, we're going to substitute that with 2 times sine x cosine x. That is the formula from the previous slide. So we have here 2 cosine x plus, and now we're going to substitute this part with the formula for the sine of a double angle. So we have 2 sine x cosine x. And then we have is equal to 0. Remember, we're solving an equation. So now you could see that both terms, and I say both because this is one term, this is the other term. Both terms contain cosine x. And what I'm going to do is factor that cosine x out of the equation, or from the left side. Cosine x. And so if we factor cosine x from here, we will get a 2. And in fact, what I want to do instead, I'm going to factor out 2 cosine x. I think that will be better. So 2 cosine x divided by 2 cosine x, from here, I get a 1. Then I have here a plus, and we have 2 times sine x times cosine x. So if we factor 2 cosine x, we still have sine x. Now from here we say that equals to 0. And now we're going to use the zero factor property and set each factor equal to 0. And then we're going to solve one at a time. So cosine x will be 0 divided by 2, which is equal to 0. So we're going to come back to that equation. Let's work on the other one. So we're going to have sine x is equal to -1. And so now, of course, we got to take the cosine inverse and the sine inverse to solve each. So I'm going to just draw my unit circle here. And whenever we need sine equal to -1, that will be at 3 pi over 2, because the sine comes from the y coordinate if we're talking about the unit circle. And so that occurs at 3 pi over 2. All right, so where is the cosine equal to 0? Well, that will happen at 3 pi over 2, but there is one more place, and that is going to be here. And that angle is going to be pi over 2. So from here we could say x is equal to pi over 2, and also 3 pi over 2. To give the general solution, remember that we have to include the solution found and then plus 2n pi, because that is the period of sine and cosine. So plus 2n pi. So we have those two values that we found, pi over 2, 3 pi over 2, and then we add the plus 2n pi, and you already know n represents an integer. So if n is equal to 0 right here, then you don't add anything. If n is equal to 1, you add 2 pi. If n is equal to 2, you will be adding 4 pi, and so on. And of course, n being an integer, it could also be a negative number. Now we're going to move on to the power reducing formulas. And here we have sine square u, cosine square u, tangent square u. So that is exactly what we mean when we say power reducing formulas. So your three formulas are here. Remember, when you are creating your formula sheet, to include those. Those will be pretty useful to have. Okay, so with the next example, example 4, we're going to use the power reducing formula. And the interesting thing of this problem is that we start with something to the power 4. So we're actually going to need the power reducing formula. We're going to use it or apply it twice. So as you can see here, we are, I guess, factoring sine to the 4th power of x as sine square x to the power 2. So this will be similar as if you had, let's say, a to the power 4, it will be a square times a square. And another way to check that is if you are multiplying, in this case, variables, you add the two exponents. So that's how the rule goes. Also, you could specify that a to the power 4 as saying a square and then square. And we know that because we have a square multiplied by itself. So it's like you're doing that a square multiplied by itself twice. And so when we have that, we could use the rule that says 2 times 2 is 4. So that will be the exponent. So anyways, with sine to the 4th power is the same as saying sine square of x times sine square of x. And another way to represent that is by using sine square like we have here, and then squaring that, just like we did here with the example with the variable a. We will be replacing sine square x with the expression that you see here on the slide. And just to verify that that is the correct one, if we look at it here, that is the same one that we're going to be using. So 1 minus cosine of w divided by 2. So we're not using the variable u to denote the angle, so we're using x. So that's why we have 1 minus cosine of 2x divided by 2. And the square, the exponent, is still there. By the property of exponents, we are going to distribute the exponent to the numerator and also to the denominator. So we will have something like that. And here we will have 2 to the power 2. So what we're going to do to expand this one, which is the next step, remember that is the product of 1 minus cosine square not cosine square, I'm sorry, cosine of 2x times, and remember this is the angle, 1 minus cosine of 2x. So it's multiplying it by itself. So if we expand that, we will be getting, and of course here, let's not forget about 2 squared, that will be equal to 4. So if we expand that, we will get 1 minus cosine of 2x, and then negative cosine of 2x times 1 will be negative cosine of 2x. And, or of course, if you know the shortcut, use it, but there's nothing wrong with going the long way. So that will be cosine of 2x times the cosine of 2x will be cosine square of 2x. And remember, we had everything divided by 4. So at this point, we will get 1 minus 2 times the cosine of 2x plus the cosine square of 2x. And of course, everything divided by 4. So since everything is being divided by 4, we could factor out the 4. But since it is dividing, we're actually factoring out 1/4. Now the other factor will be just made out of the numerator, the stuff that the whole expression that we have there. So it will be 1 minus 2 times the cosine of 2x. That's what we have here. And then plus cosine square of 2x. So that is our numerator, and the 1/4 is what used to be the denominator. Since we have cosine square of 2x, we're going to have to use the power reducing formula one more time. So just to, I'm going to write the formula that we have here. And I want to show you how when we have cosine square u, it does say u and not 2u. Now we're going to use one that it says, well, or what we're going to need to replace is going to be cosine square of 2x. So instead of u, it's 2x. So what's going to happen when we actually use the formula is that instead of just doubling this angle like we did here, well, we're still going to be doubling it, but it's going to be 2x times 2. And so for that reason, we're going to have 1 plus the cosine of 2 times 2x, so that will be 4x, and then divided by 2. So that is the reason I'm saying equal to 4x when we use it on the problem. So remember, and since we're doubling the angle 2x, that's why we're going to have 4x. And Again, the reason we have to use the reducing formula again is because we have cosine squared here of 2x. Now, the substitution of the expression that we have here, we already know it was substituted with that one, and you could see that on the next slide, the one that I am highlighting. So what we're going to do from here is use the distributive property. So 1/4 times 1, 1/4 times negative cosine of 2x, and 1/4 times the fraction here. So that's what we're going to write. And we're going to have 1/4 minus 2/4 of the cosine of 2x, and then plus 1 plus cosine of 4x divided by 2 times 4, which is 8. Now from here, we're going to simplify it a little bit. So now we have 1/4 minus 1/2 and here this one will be the same. And here keep in mind that the 8 is dividing the number 1, and also dividing cosine of 4x. Now we're going to factor out the common factor, since we have terms that are just numbers without a trigonometric expression. Our common factor must be a number, and it's actually going to be the smallest fraction that we see here, because that fraction can divide 1/4, it can divide 1/2, of course it could divide 1/8, and of course it could divide this one. Imagine it has a 1 over 8. So we're going to divide by 1/8, and if we divide 1/4 by 1/8, so I'm going to do the scratch work over here. We have 1/4, and we want to divide by 1/8. So that is actually going to turn into 8 divided by 4, which is 2. So we have a 2 here. The next one will be, we're going to factor from this term 1/8. So if we consider the 1/2 and divide it by 1/8, that one is going to give us 8 divided by 2, which is 4. So this will be minus 4 cosine of 2x. And then finally, if we, almost at 1/8, and we factor out 1/8, then we will have a plus 1. And the final term that we need to factor 1/8 from will be the one here. So if we take out the 1/8, we would still have the cosine of 4x. So that's what happens. Now we're going to combine like terms, and that will be the plus 2 and the plus 1. And so when we do that, we will get a plus 3. We could see that there. The next term, negative 4 cosine of 2x, is here. And then we have the positive cosine of 4x, and that is here. Now, don't think, please don't do this. Don't say that you could add the 2x and the 4x and say this will be something like cosine of 6x. Don't do that. That is wrong. So please don't do it. They are different angles, and so we don't want to do that. It's just something you don't do. So don't do it. Okay. And so you can see that the 1/8 that we factor out is still carrying out here. And so maybe you forgot what we were trying to do, but it's right here to remind us that that is the answer that we got, and the question was here. The sine of to the fourth power of x, which remember this is equivalent to saying something like sine of x to the power 4. So the graph is here. If you were to go to your graphing calculator and enter one like that, and this is what you could do to verify your work, and enter sine to the power 4 of x, and if we enter on y sub 2, we will enter the expression that we see here. And so if you do that, you should get the same graph. Now, when you are entering something like this on the calculator, I would recommend that the 1/8, you enter that as a in parentheses. So parentheses 1 divided by 8, close parentheses, then you will enter the rest. 3 minus 4, and then you can press your cosine key, and then in parentheses, make sure you do enter 2x in parentheses, close parentheses, then plus cosine with the cosine key, and then parentheses for x. And then here you are actually going to close with a double parentheses, one to enclose the angle for x, and another one to enclose this one, the one that is in front of the number 3. So be careful when you do that. Make sure you do include x. And then if the two graphs overlap, that means that you have the correct answer because they are equal. And why did we do that? Well, because the question was to use the power reducing formula so that it wouldn't be sine to the power 4, and it was just the first powers of sine of cosines. So that is why we ended up with that, cosine to the first power and cosine to the first power. The next group of formulas we have here are the half angle formulas. You can derive some useful alternative forms of the power reducing formulas by replacing u with u divided by 2. The results are called half angle formulas. So we're not going to derive those, but we have them here, and we have sine of the angle u divided by 2. So that's why we call it half angle. And so the formula will be here, the square root of 1 minus cosine u divided by 2. And we have the positive and the negative signs here, but not that you could have both. You just have to make a decision based on where your sign of the double angle will land on, where the terminal side will be with respect of the half angle. And so, but we'll learn how to do that. And then of course we have one for the cosine of u over 2. So that's here. Same thing with the signs, positive or negative. It depends where that angle is. Remember that in quadrants 1, 2, 3, 4, sine, this one is positive, and quadrants 1 and 2, negative in quadrants 3 and 4. Then cosine is positive in quadrants 1 and 4, but it's negative in 2 and 3. And finally, tangent is positive in quadrants 1 and 3, and negative in quadrants 2 and 4. So that's what we mean when we said depending on the quadrant in which the half angle lies. And then we also have the one for tangent here of u over 2. And we do have two options here. And those two are the same. In fact, it was one of those identities that perhaps you had to prove or something. And we can go from one to the other version just by multiplying by the term. Let me show you. Maybe you will remember what it is. So this will be sine of u. And if we were to take that and multiply by 1 plus cosine u over 1 plus cosine u, then we will arrive to this one here. In example 5, we're going to use the half angle formula to find the exact value of sine of 105 degrees. So 105 degrees is not one of our common angles that we know the sine of right away. We'll have to use the calculator. However, for these questions on WebAssign, you will have to use the formula. And the formula that we will be using is the half angle formula for sine of u divided by 2. So let me write what the formula is here. And this is something you should get used to it. And we will have here, the formula will be the square root of 1 minus the cosine of 2u divided by 2. And we also have something like positive and negative. And that is the formula from the previous slide. We have it here. So if we think of u over 2 is equal to 105 degrees, then u will equal to 2 times 105 degrees. And that will make u equal to 210 degrees. So that this part here, 2u, okay, I don't think I have the, okay, so the formula is not 2u. We actually need to fix this. And I'm just gonna erase the whole thing. Something's happening. Sorry about that. So I was able to correct that mistake. This is supposed to be u, and this is u over 2. So what we had done here, that was correct. And so u, and you could confirm by looking at the formula here, it says 1 minus cosine u. So if we come here, we're gonna see the substitution already there. Now, why are we using 210? Well, because 210 has a reference angle, which is in standard position. If we graph it, it will start here and then counterclockwise. So it's going to go 180 and then 30 degrees more. So the terminal side will be in quadrant 2. This is angle 210. Now, when we and I said that we use it because the reference angle is one of the special angles, which is 30. Now, the angle that we're trying to calculate sine is 105. Now, 105 in standard position starts on the positive x, counterclockwise, goes up to 90, and then 15 degrees more past 90. So in that case, for the angle 105, we're going to say that the terminal side is in quadrant 2. So for the sine of 105, it's going to be positive. So from the square root, we will choose the one with the positive answer. Okay, so since we need the cosine, of 210 degrees. So we use the reference angle of 30, and the cosine in quadrant 3 is negative. So it's going to be negative square root of 3 over 2. Because the cosine of 30 is the square root of 3 over 2. But since we're in quadrant 3 for the angle 210, then for that reason it is negative. And then we are dividing by 2 here. So here we're going to clear the negative signs. 1 plus the square root of 3 over 2, and everything's divided by 2. So what we're going to do next is add the 1 to the square root of 3 over 2. The 1 in terms of halves, it is 2 over 2 plus the square root of 3 over 2. Now that they both have the same denominator, as you can see here, 2 and 2, we could put them both under one fraction. And so that will be the square root of 3, the square root of 2 plus the square root of 3 over 2. And then we are dividing by this 2 here, so I'm not so sure what happened with that one. Okay, I'm going to pause the video and figure this out. Okay, so I know what happened. So everything that we have here is still inside the radical. So everything is inside the square root. So we're going to multiply the outer quantity. So that will be 2 plus the square root of 3, like that. And then the inner quantities. So that will be a 4. Now, what we're going to do is that here we have the fraction inside the square root. So now we can do the ratio of two square roots as well. And so what happens here is that the square root of 4 gives us 2. And then this one, we just keep it that way. So it was the square root of 2 plus the square root of 3. And that is what we have here. That's the square root. And then inside that, we have the 2 and the positive square root of 3. The next group of formulas are the ones called product to sum formulas. And here when we say product, we are referring to the multiplications going on here on the left side of the equal sign. Those are products. And what happens is that we turn them into the sum of two trigonometric expressions. So you can see here clearly plus plus or minus minus, and think of addition as the combination, not combination, but the fact of adding and subtracting. It could be looked at as the same operation. So that's why we just call them that, even though we're subtracting here and here. Okay, and so sometimes we will be using those. The product to sum formulas are used in calculus to solve problems involving the products of sines and cosines of two different angles. So for example 7, we're going to use one of those. And we have the instructions are rewrite the product cosine of 5x times sine of 4x as a sum or difference using the appropriate product to sum formula. So we're going to go here, and as you notice, the product is cosine and then sine. So the one that looks like it is the last one here. So let's go ahead and number them, 1, 2, and make sure you do write this in your notes. It also goes to your formula sheet. So make sure you have that. So we're going to use that formula, number 4. Let me just write it down here again so we could see it. So cosine of u, sine of v is equal to 1/2, bracket, sine, parentheses, u plus v, parentheses, minus sine of u minus v, and close the bracket. Okay, so using the appropriate to product sum formula, we obtain. So first, let's look at our angles. So here we have u, and then we have v. Now, with our problem with example 7, angle u happens to be 5x, and angle v happens to be 4x. So that is what we're going to be substituting into the parentheses here. So let's do this. So we're going to have 1/2 bracket, and then sine of this first angle here, 5x, and then we have a plus here, and then the second angle, which is 4x, close parentheses, then we have a minus from the formula, and then we need sine of the first angle, which is 5x, and then minus, and we have here the second angle, which in our case is 4x. So now we simplify. Oh, and the substitution was already here. So we simplified, and from here, from 5x plus 4x, and that is how we get 9x, the 9x that you see here. And similarly with the 5x minus 4x that we wrote down here, that is how we get just 1x. And the 1/2, what's happening here is that it's being distributed, because the 1/2 is multiplying this expression and also the second one. So that's why you could see 1/2 times sine of 9x minus 1/2 of sine x. And that will be the solution. So remember, the question here was to rewrite the product as a sum or difference. So that's why here we don't have sine multiplying sine or cosine multiplying sine. It's just the sum, or in this case the difference, of two trigonometric expressions. Just like we had the product to sum formulas on the previous slide, we could see on this slide that we are going to have the sum to product formulas. And we call them that because first we have a sum or a difference, but remember that's the same operation. Subtraction is the same as adding, but negative numbers. And so with sum, we turn those into products. So you could see how here sine is multiplying to cosine. Here we have cosine times sine. And here we have cosine times cosine. And then we have sine times sine. And it's important to notice that we have a negative sign here in front of the expression. So please keep that in mind. And of course, these formulas need to also be added to your formula sheet. Okay, so for the application problem, example 10, we're going to look at this projectile motion. And so ignoring air resistance, because if we were not to ignore air resistance, then none of these equations will work. The range of a projectile fired at an angle theta, remember that's the Greek letter, with the horizontal and with an initial velocity of v sub 0 feet per second is given by the equation r is equal to 1/16 times the initial velocity, the v sub 0, or the velocity at time 0, being squared, and then times sine of theta times cosine of theta. And here we're being told that r is the horizontal distance in feet. So the inputs here will be, of course, theta, well, more specifically sine of theta and cosine of theta, but yes, theta. And also the initial velocity is going to have to be given to us. And the output will be the horizontal distance. Of course, if we were to be given the horizontal distance, perhaps we could find the angle. Okay, so on the example that we're going to solve, it says a football player can kick a football from ground level with an initial velocity of 80 feet per second. So right here, that is given to us, initial velocity. So we will say that p sub 0 is equal to 80 feet per second. And also, let's just make this clear. R is the horizontal distance, and theta is the angle with the horizontal. So if the ground or the grass was here, and here is the guy kicking the ball, I don't know if it's the kicker, and so the angle at which he is going to make like that with the football, that will be theta. So the first question is, write a projectile motion model in a simpler form. And we're going to use the double angle formula to rewrite the projectile motion model. So I have copied the equation that we had from here. And what we're going to do is substitute the initial velocity with 80. So I'm going to just erase that there, write down the 80. And by the equation, we are supposed to square that one. Okay, in fact, we're not going to do that because here we just need the model. So I'm sorry about that. We're just gonna leave the initial velocity there as a variable for this part of the question. So instead, what we are going to do is try to think of an identity that contains sine and cosine. And I don't want you to think about all the difficult ones, such as the product to sum. I'll show you which one, sine, cosine. We don't want this one. We want something that might look easier, something like a double angle. And that one is actually one of the first formulas from the section. And not that one, right here. We want to have sine of 2u as the 2 times sine of u cosine u. So that's what we're going to need. So based on the number that I need to make up for here in my expression, and so far this is what we have. R is equal to 1 over 16, and initial velocity square times sine of theta cosine theta. So since we want to have that 2 in front of this product, we're gonna do this little trick. So 1 over 16, if we multiply by 2, top and bottom, what we will obtain will be 2 over 32. Now, what could we do here? Well, the 32 could be placed in the denominator of the model. And then the 2 that we have here, that we needed, it could be placed here. So that is what happened. Now, this whole expression corresponds to sine of 2 theta, just like we have it here. Sine of 2 theta. And so that will be the answer to that question, which was write the projectile motion model in a simpler form. And for part B, it says, at what angle must the player kick the ball so that the football travels 200 feet? So now the question says, and I already have the substitution here. So the question is asking us, what is theta supposed to be? That is the question. And remember, we were given the initial velocity of 80 feet per second. And so the initial velocity is being substituted here. Then it's telling us that at what angle, so that the horizontal distance is 200 feet. And so that is equal to r, remember, horizontal distance. So to solve something like this one here, we will have to use some to do some algebra. So let's see. We could start by multiplying 200 times 32, and then that will be equal to the square of this one. So it's like 80 times 80, and that will be 6,400. And that will be times sine up to theta. So one of the things I could do here, if I multiply 32 times 200, I could multiply 32 times 2, which is 64, and then I'm going to have the times 100, so with 2 extra zeros. Then here, this 6,400 is multiplying sine of 2 theta, so if I take it across, it's going to be dividing. Okay, and now we just have sine of 2 theta here. So that is how we simplify it. And we all know that here, this is gonna equal to 1. So we have 1 is equal to sine of 2 theta. And so if we take the sine inverse on both, we will get that 2 theta is gonna be the sine inverse of 1. And let's see in what quadrant is the sine equal to 1. And that actually it happens at pi over 2. And that one is the solution of 2 theta. And we want to find what theta is. So we have it here as well. That's the solution of 2 theta. And so to find theta, we have to solve this equation here. So that will be theta is equal pi over 2 divided by 2. So remember, when you divide by 2, it's like you're dividing by 2 over 1. So this is going to be pi divided by 4. And that is what theta will be. And so pi over 4, if WebAssign is asking you to submit your answer in degrees, you should know at this point that pi over 4 is 45 degrees, or you could convert it, and so the answer will be 45 degrees or pi over 4 radians. With that, then we could ensure that the horizontal distance is 200 feet with an initial velocity of 80 feet per second.